Hello, in this second lecture on the PIC microcontroller 16F877, we'll discuss few more details about the device. Here we are going to study in details its data memory. We'll discuss the different special function registers. Particularly, we'll discuss the SFRs like status register, power control register in more details. Then we'll discuss the different addressing modes that are used for its data memory. And finally, we'll discuss in details the I/O port section of this microcontroller. So let us begin. Currently we are discussing this microcontroller, PIC microcontroller 16F877. We have discussed the different family members, particularly which are lying at the highest level in this family, and the device which is lying at the highest level is 16F877. This microcontroller has all the features which are typically available in this PIC family. Okay, so at the beginning we are discussing this particular device which is lying at the highest level in this family of the PIC microcontrollers. We have seen that this microcontroller is 40 pin IC, and there are various pin signals as we have discussed last time. Then we have seen its program memory. We have discussed its program memory last time. It has 8K kilo cross 14 bit type of program memory. We have seen that. Okay, then last time we started discussing with the data memory. This particular microcontroller has in all 512 bytes of data memory. 512 bytes of data memory, and that is available in 4 banks: bank 0, bank 1, bank 2 and bank 3. Okay, each bank contains the whole 112 bytes is divided into 4 banks. You can see that the memory the address of the various locations in the memory goes from 0000 to maximum 1FF. So the address is actually 9-bit address, right? 4 plus and 1, so 9-bit address. Okay, so the address range in the first bank is from 000 to 07F. After 07F it is 080 in the bank 1. It ends at 0FF. Okay, so after 0FF the next address is 100. It goes up to 17F, and after 17F it goes to 180 up to 1FF. So that's how these addresses are provided to the various memory locations in this data memory. So this is a read-write type of memory. It is used for temporary storage of data. It's a volatile memory. That means the information will be held in this memory as far as the power supply is on. Okay. What you observe here is that there are various SFRs, special function registers, and there is some area which is used for general purpose storage. First of all, let us see how the addressing is done. Okay, there are two types of addressing modes. One is direct addressing and indirect addressing. Okay, so let us discuss that first. Okay, the question is how an instruction addresses one particular location in this memory. Actually, if you consider the status register of this microcontroller, it is of course present in this memory bank itself. You can see this is a status register here. Then that status register is a 8-bit register, and bit pattern of the status register is like this. it contains these 3 bits which are used for bank selection. Okay, rest of the structure of this particular status register is identical with that which was available in the lowest device which we have already studied, 16C61 microcontroller, which we studied in the last semester. So carry flag, direct digit carry flag, 0 flag, timeout bit, power down bit. The functions of all these bits is same as we have seen in 16C61. In 16C61 there were only 2 banks. Okay, and therefore only one bit was available there, RP0, as bank selection bit, right? When that bit is 0, bank 0 is selected, and when that bit is 1, bank 1 is selected. That was the case in 16C61 device. But here, because there are 4 banks, basically these 2 bits are provided to select one of the 4 banks. Okay, so RP1 and RP0 are bank selection bits. Okay, so we can see that in particularly direct addressing mode, say there are 2 addressing modes as usual, direct addressing mode and indirect addressing mode. In the direct addressing mode, as you can see here, with help of these 2 bits, one of the bank is selected out of the 4 banks. Okay, and the 7-bit address of one of the locations in the bank is actually provided as a part of the opcode. Okay, you know that the instruction, every instruction of this microcontroller is 14-bit wide. Every instruction is 14-bit wide, and therefore those 14 bits, they contain the code of that operation of that instruction corresponding to that instruction, and it also contains the address of the data or address of the location in the data memory for the operand. Okay, so if you can understand that. So there is a 14-bit instruction. So instruction is 14-bit. So out of the 14 bits, the last 7 bits, bit 0 to bit 6, they represent the address of the memory location, address of memory location in the given bank, in the selected bank, in the bank. Okay, so that's how this 7-bit address is obtained from this opcode of that instruction, as is said here. And bank selection is done by these 2 bits. Okay, so you can understand that if one bank is selected, then that bank contains 128 locations. 128 locations having address, say for example 0027F, 128 locations. And to address 128 locations, you need 7-bit address. Okay, because 2 raised to 7, as you know that 2 raised to 7 is 128. And therefore 7-bit address is needed to address one of the locations from this bank. Okay, so that is provided in the opcode as we have seen here, this part. Here, 7-bit address. Okay, and one of the banks is selected with help of RP1 and RP0 bits. Okay, so that is what is called as direct addressing mode. Direct addressing mode. The address of the operand is directly given in the instruction. The only requirement is that you have to select one of the 4 banks with help of bits RP1 and RP0. Okay, now there is another addressing mode called as indirect addressing mode. In that case, the address of the operand is placed in a register which is file selection register, FSR, and FSR is an 8-bit register. Okay, so out of the 9 bits of address which is required for actual 9 bits which is required for selection of a given location, you know this is a 9-bit address. Out of the 9 bits, 8 bits will be held in that FSR register, and 1 bit is held in another bit of option register. We will see that. So, in the indirect addressing mode, what happens is like this. The FSR register holds 8 bits of the address, and the 9th bit is held in this particular bit. This is called as a bank pair selection bit. Okay, it selects a pair of banks. Right. For example, when this bit is 0, it is in here. Banks 0 and 1 are selected, and when this bit is 1, then banks 2 and 3 are selected. See, for example, if this bit is 0, then bank 0 and 1 will be selected, and the total number of locations in bank 0 and 1 together is 256 locations, 128 plus 128. And to address one of the 256 locations, you need 8-bit address. Okay, because as you know, 2 raised to 8 is 256. Right? So 8-bit address will be required to select one of the locations in a pair of banks. Okay, and that pair of banks is selected with help of bit IRP. Okay, so this is bank pair selection bit to select a pair of banks, and this 8-bit address in the FSR register selects one of the locations in this pair. Okay, so that's how the indirect addressing mode works. Okay, so you may select bank pair 01 or 12, and the remaining address will be provided in the as a part of the opcode. Sorry, will be provided in the FSR register. Okay, is it clear?
Yes, sir.
Okay, so this is similar to the technique which is used in that device 16061 also. There also FSR register is used to hold the address in indirect addressing mode. Okay, so that is what we have seen, direct and indirect addressing mode. Now once we go back to the register banks, when you look at this, you can understand that many registers are the SFRs, special function registers. See, in the device 16061, there were only 2 banks. Right? There were only 2 banks. These 2 banks were there, and very few number of SFRs were there. So if you compare these 2 banks, bank 0 and bank 1, with the corresponding banks in your 16061 microcontroller, then you will realize that the distribution of the different SFRs at the different addresses is same as it was there for 16061. Okay, for example, the addresses of timer 0, PCL, status, port A, port B, etc. These were present in the device 16061, and their addresses were also similar to this, same as this. And therefore, the registers which were seen in the lower devices, they are carried forward as they are without any change. But in addition to that, there are some additional many SFRs. Okay, you can you just try to understand that the different SFRs, they are associated with different functional blocks of this microcontroller. In the lower devices like 16061, many functional blocks are missing; they are not there, and therefore corresponding SFRs were missing in the register banks. But in the highest device which we are discussing currently, all the functional blocks are present. For example, timer section, full-fledged timer section, serial communication section, ADC section, parallel communication section. All these sections are present in this highest device, and therefore different sections will have their own SFRs, and all those SFRs, they are seen in these banks, bank 0 and 1, as well as bank 2 and bank 3. bank 2 and bank 3. Okay. If you want to see how the registers SFRs are associated with the different functional blocks, you can for example understand that there are some basic SFRs which are for example your status register, another FSR, PCL. These are basic SFRs. There are some SFRs which are associated with the port section. You can see port A, port B, port C, port D, etc. Okay, there are some SFRs which are associated with the interrupt operation, interrupt control SFR. Okay, there are some SFRs which are associated with maybe capture, compare, PWM modules which are present in this particular microcontroller. Some SFRs are associated with the serial communication section like TX register, RX register, etc. Some are associated with the ADC section. Okay, so these are the different SFRs which are associated with the different functional blocks. If you actually want to see the distribution, you can see it like this. Out of the different SFRs, see there are total 53 SFRs available. There are total 53. If you see the total, if you count the total number of SFRs, they comes out to be total 53 SFRs. Of course, you can understand that some SFRs are repeated in different memory banks. Okay, some are repeated. For example, status register is seen in all the memory banks. Okay, the strategy is like that. The registers which are needed very often, they are provided in more than one register bank. Okay, some registers can be seen only in 2 register banks. Some can be seen only in 1 register bank. Okay, the SFRs which are needed very rarely, they are provided only in 1 memory bank. Okay, but if you count the total number of different kinds of SFRs, then that number comes out to be 53. And those 53 SFRs can be grouped as shown in this slide. Okay, just now we have seen that there are some basic SFRs like program counter lower, PC latch, option register, status, power control register. Okay, then for IO section, there are SFRs associated with the different IO ports. We have seen that in this microcontroller there are in all 5 IO ports, A, B, C, D and E. Okay, corresponding to every port there is a TRIS type of register. Okay, this register is used to configure the given port either as input port or output port. So these are also additional SFRs. Okay, so these are associated with the IO section. For example, for timer section, this microcontroller has in all 3 timers, timer 0, timer 1 and timer 2. And every timer has its own set of SFRs. For example, if you consider timer 1, then there are 2 registers which are count registers which can hold 16-bit count. This is a 16-bit timer. And 1 register is there which is used to control the operation, timer 1 control register. Right. Similarly, timer 2 is an 8-bit register, 8-bit timer. So it has 1 register as a count register, and T2 control, timer 2 control register is used as control register. Additional register is required for that PR2 register. So that's how these registers are associated with timer section. So if you go for interrupt section, then there is one register called as interrupt control register. It basically contains all the bits which are used typically to control the interrupt operation. Okay, and there are certain registers called as peripheral interrupt enable register, peripheral interrupt flag register. Okay, so these are also associated with the interrupt section. We will discuss them one by one when we come to the corresponding section. Okay, so this is how we can see that SFRs, ADC section, analog to digital converter. You know that this microcontroller contains 10-bit 8-channel 10-bit ADC. Okay, so that ADC needs some registers. For example, it has 2 registers here, you can see, which can be used to store the result. Okay, because it's a 10-bit ADC, the result cannot be stored in a single register. Single register is only 8-bit, and therefore 2 registers are provided. Out of that, 10 bits are used to store the result. There are some registers which can control the interrupt operation. So that's how there are different registers which are shown in this list, which are associated with different functional blocks. Now we are going to discuss the compare capture CCP modules in details. We'll come across these particular registers when we discuss them. There are two modules available in this microcontroller. Okay, so that's what we see, that the total 53 SFRs which are available can be grouped under different categories depending upon how they are related with the different functional blocks. Is it clear?
Yes, sir.
Okay, so now we can proceed further. Now we have to discuss the different SFRs one by one in the details, and we'll discuss the different functional blocks, and also when we discuss that block, we'll study the related functional SFRs which are related to that particular functional block. Okay, so let's begin with the most basic SFRs. So when we start with basic SFRs, one of the basic SFR, as we have seen, is status register. This we have already discussed. Okay. Then we'll go to the option register. Another basic SFR is the option register. The structure of this option register is exactly identical with the structure of the option register in the microcontroller 16061. Okay, and that we have already discussed. Okay, so we just copy and paste from that discussion, from last semester discussion. Okay, so we have discussed all these bits, their functions. Okay, same function here also. No change in the option register. Okay, the next register which can be called as a basic SFR is power control register. The power control register contains 2 bits. Okay, most of the bits are not used. These 2 bits are used to indicate the different situations under which the reset has occurred. You know, there are different ways in which you can reset your microcontroller. Like you can apply the reset in signal, or when the power supply is switched on, the microcontroller is automatically reset, or when the power supply goes below certain voltage. Typically, see, normal voltage of the power supply required is 5 volts. But when the voltage of the power supply goes below certain level, maybe typically 2 volts, then the microcontroller is automatically reset. That is called as brownout reset. Okay, there is the reason for resetting, that when watchdog timer matures, it resets the microcontroller. So there are various ways in which your microcontroller can be reset. Here 2 bits are provided to indicate 2 particular reasons for resetting of this microcontroller. One is power on reset, other is brownout reset. You know, when you switch on the power of the microcontroller, we have seen that internally that microcontroller has a power on reset circuit. The internal circuit senses that the power is getting on. Okay, and it resets the microcontroller, because it is essential that whenever you switch on the computer system, the system should be reset initially. Okay, that means initially all the registers, counters should be cleared, and because computer operation is a sequential operation, it should always begin from the initial status. Okay, and therefore to ensure that the microcontroller is required to be reset when the power supply is switched on. It gets automatically reset because of the internal circuitry, but when that happens, this particular bit will be reset. Okay, so this is active low bit. So when this bit is 0, it means that the reset has occurred because of power supply on, switching the power supply on, power on reset. Okay, similarly other bit is provided here to indicate that the reset is because of brownout condition. Brownout means when the power supply, suppose the microcontroller is working normally, power supply is 5 volts, and suppose it is battery operated, and if the power supply voltage goes on decreasing as the battery drains out, if it is not charged periodically, then the voltage of the battery may go down, and if that goes below some dangerous level, maybe say 2 volts, then automatically this microcontroller is reset. Okay, and when it is reset, then this particular bit becomes 0. Okay, so by checking these 2 bits, the programmer can understand what kind of reset has occurred, whether it is power on reset or brown out reset. Okay, so you can say that these bits are set or reset by the hardware. These are not to be set or reset by the programmer. These are to be set or reset by the hardware of the microcontroller, and they get set or reset depending upon the corresponding situations. Okay, so these are the basic SFRs. Is it clear? Hello, Gayapode?
Yes, sir.
Okay. Okay. Now we'll go to the next set of SFRs. Okay, instead of going through as per SFRs, let's go as per the different functional blocks. Okay, now let's discuss the IO section. Let us discuss the IO section. Let us discuss the IO section. Okay. As you know that there are in all 5. Okay, what we are discussing now is the IO section, input output section. You know that there are 5 IO ports in this microcontroller. They are named as port A, B, C, D and E. Okay, so we have seen that port A is a 6-bit port. Port A is a 6-bit port. Port B, C and D are 8-bit ports, and port E is a 3-bit port. Okay, so that's how 33 IO lines are available in terms of these ports. This we have seen. Now let us see the different features of the different ports one by one. So suppose we begin with port A. Okay, so as we have seen that it is an 8-bit port. Okay, the port A can be configured as either input port or output port. Input port or output port. So the IO function of this port is decided by the tris A register. This you have discussed last in the previous microcontroller also, same as that. There is an 8-bit tris register, as you know. By setting a bit in tris register, you configure the corresponding bit of that port as input bit. Okay, and by setting the bit in the tris register to 0, by clearing the bit, you set the corresponding bit of the port as output bit. You know that, same as before. Okay, then port A is a general purpose port. It can be used as to read 8-bit data or write 8-bit data, read-write operation, general purpose. General purpose. That is about port A. As you know that inside the microcontroller, there is a latch for every port bit. Okay, so this is an 8-bit latch, you can understand. So this will be an 8-bit latch. 8-bit latch. And whenever some data is outputted, that data is latched here and that bit is outputted. Okay, so that means when you output the data, 8-bit data, So you have to write into the latch of the port, and that data is outputted. So that is output function. But when you want to read the port, actually what is read is not the status of the latch, no doubt this is stored here, but what is read is the port pins are read. Okay, port pins are read. Okay, so write operation writes the data into the latch, and read operation reads the data from pins of the port. So whatever status you apply here from outside, that will be read. So that is obvious, because you are not supposed to read the data which is there in the latch. Okay, previously you might have outputted some data to the latch. That you don't want to read. You want to read the status of the pins, because the data is to be supplied from outside, and that data has to be read. So read operation is read the pin, read pin operation, and write operation is write to latch operation. Okay, so these are the two different things, as you understand. Okay, so that is generally applicable to any port. Okay, that is about port A. Okay, now we'll go to port B. Port B was also available. In your previous microcontroller. It's an 8-bit port. Port A is a 6-bit port, right? Port B is a 8-bit port. Associated with that, there is, as you know, that for deciding the I/O function, there is a tris-B register. Available. You can set or you can configure the port as input or output with help of this. Then speciality of port B is that all the port pins of port B have internal pull-ups, weak pull-ups. Okay, so whenever you configure the port B as input port, right, then those pull-ups are enabled. So every every pin is internally pulled high through a weak pull-up. This is what we have discussed already for 16661 also. And therefore, if you leave an input pin open, that status of that pin will be considered as logic 1. Okay, because of the internal pull-up. Okay, so that means you simply have to connect an external switch connected to ground to make the pin low. Otherwise, if you leave it open, it will be considered as logic 1. So that are the weak pull-ups. These weak pull-ups can be turned on or off. So when the port is input port, for the input port, there are weak pull-ups, right? Weak pull-ups, and they can be switched on or off, or enabled or disabled. They can be enabled or disabled through software. Oh no, there is a bit in your option register, and that bit allows you to, RBPU. This bit allows you to switch on the pull-ups or enable the pull-ups or disable the pull-ups, that you know. Okay. When you configure a port as output port, these pull-ups are automatically disabled. Okay, so that is about weak pull-ups. One more feature that this port B has is that what we call as port B change interrupt. Port B change interrupt is another feature, and that feature is applicable particularly to input pins PB4 to PB7. Okay, so for the input pins, when you configure these particular pins as input pins, okay, then this particular feature is applicable to these pins. We know that whenever any of these pins makes a change from high to low or low to high, the CPU is automatically interrupted. Okay, and in the ISR, you can write instructions to read the port and to find out which particular pin has changed the status. This particular facility is provided, as you know, typically for interfacing matrix keyboard to the port B. Okay, port B, you can apply the matrix keyboard. As you know that the rows and columns, rows are scanned, columns can be connected here, right? Whenever you press a key, the status of this one of these pins will change, and that will tell the processor that one of the keys is pressed, and the processor can read this port to find out which key is pressed. I think these features are same as we have discussed for port B in your 16061 microcontroller. Is it clear?
Yes, sir.
Okay. Next is port C. Okay, the addition, see, this port was not available in the lowest device. Now we are going to have the port numbers, third port, which is port C. Okay, port C is also 8-bit port. It also has TRISC register to set this port either as input or output port, right? Okay, now the special feature of this particular, see, this is also used for general purpose I/O of data, used for general purpose I/O of data. Okay, the one special feature provided to port C is that it has Smith trigger input buffers. It has Smith trigger input buffers. Okay, that means when you configure any of these pin as input pin, then that input pin, for example, if you consider PC RC0 pin as input pin, then this pin will have Smith trigger input feature. As you know that in Smith trigger operation there is an hysteresis. Okay, so if the voltage, when you change the voltage applied to the pin from say low level to say high level, and then after high level to the low level, then you know that unless and until it goes above UTP, the output it will not be considered as logic 1. So it will be considered at logic 1 when it goes above UTP, and it will be considered as logic 0 when the voltage goes below LTP. So that is the property of a Smith trigger. Okay, so actually the microcontroller will sense that the pin has gone high at this particular instant and the pin has gone low at this particular instant. Okay, and therefore this will be considered as the logic input, right? Logic input. So even though the actual voltage is changing gradually and there is maybe some noise superimposed on this waveform, because this may be coming from some sensor, some transducer, and maybe during propagation of the signal along the cable it may pick up some noise, and this waveform may not be strictly TTL type. Okay, but because it has Smith trigger input facility, it doesn't matter. The waveform shaping will be automatically done, and the microcontroller will not get confused because of this random change in the waveform. It will consider the input strictly as logic 0 up to this and strictly as logic 1 in this region. So that is the advantage. So this provides effectively what is called as the noise immunity. This provides the noise immunity. Noise immunity during receiving the data. Okay, that is about port C. Okay. Now let's go to port D. Port D is also 8-bit port. Port D is also 8-bit port. Port D is exactly identical with port C. Port D is exactly identical with port C. That means it's an 8-bit port. It has a register called as TRISC D register, right? It has Smith trigger input. Smith trigger input. So normally used for general purpose I/O. Normally used for general I/O, inputting and outputting of data. That is about port D. Okay, but port D has one additional feature. Port D has additional, maybe you can call it as an alternate function. Port D has an alternate function, and that alternate function is that your port D can work as a parallel slave port. Parallel slave port. It is called as PSP. So port D has PSP feature. PSP feature. We'll see exactly what it means. Actually, in short, this when you operate port D as parallel slave port, it is possible that this port can receive 8 bits of data in parallel with handshake from some external input device. So when you are operating port D as PSP, it is possible to receive the data with handshake. You can understand that none of the ports of this microcontroller has handshake facility. We have seen that such handshake facility is available in the ports of the 8255 PPI. Okay, but here no port has this facility, but port D is provided with this kind of facility, at least partial type of facility with handshake signal is provided, and that is when it operates as PSP. Okay, now question is how to operate this port as PSP. There is a bit in the bit is PSP mode bit. PSP mode bit. There is a bit in TRIS-E register. In TRIS-E register. Actually, TRIS-E register is associated with port E. We are going to discuss port E after this, and that will be normally used to set the port E as input port or output port. But some of the bits of port E are used for TRIS-E register are used for some other function. One of the bit is PSP mode bit in that register. When this bit is set, then your port D operates as output port. It operates as PSP port, parallel slave port. And when this bit is reset, then port D will operate as normal I/O port. Normal I/O port. Okay, so if you want to operate port D for normal I/O, then this particular bit should be reset. But when you want to operate this port B for as PSP, this bit should be set, and then the port can work as PSP port. Is it clear? Okay. Okay. Now we'll discuss the port PSP operation in more details after we discuss TRIS-E register particularly. Okay. So for that, let us go ahead for port E. Let's go ahead for port E. Okay. As we know that port E is a 3-bit port. It has a register TRIS-E which can be used to configure that port as input port or output port. Okay, so this port E is 3-bit port, but it has Smith trigger input facility. Smith trigger inputs facility. Okay, otherwise it is used for simple I/O of data. Normally it is used for simple I/O of data or I/O of data. Of course, it will be 3-bit data only because it's a 3-bit port. Okay, that is the basic function of this port. That's all. Okay, now when you look at the TRIS-E register, we'll notice that See, actually it's an 8-bit register, but 3 bits of this register will be used to set or reset, used to decide whether these 3 bits of port E will work as input bits or output bits, and the remaining 5 bits of TC register are used for some other function, and that function is typically related with PSP mode of operation of port D. So that's how these two ports are interlinked. Okay, so now let us discuss the actual structure of tree C, so that you will understand how tree C register is used for PSP mode of operation of port D. Okay, so for that you can look at this particular structure of your TRIS E register. This is the structure of TRIS E register. When you look at this, you can see that it's an 8-bit register. It's an 8-bit register. It's an 8-bit register. The lowest 3 bits are used as data direction bits for port E, because port E is a 3-bit register, as you know. E is a 3-bit register, 3-bit port in fact. So to configure each of these bits as an input or output, these bits are used as TRIS E bits. This is a normal function of the TRIS E register. Now remaining bits, as you can see here, are used for the PSP mode of operation of port D. These are used for PSP mode of operation of port D. As before, we have seen that PSP mode bit, when it is set, then port D will work as PSP port. When it is reset, the port D will work as simple IO port. Okay, if you make PSP bit 0, for example, that means you are configuring your port D for general purpose IO mode. In that case, these 3 bits will be don't care bits. These bits will not be used, and your TRIS E register will be used only for setting the data direction for port E. Okay, हे बीट जर 0 असेल तो हे दोन बाकीचे बिट्स हे डोंट केअर बिट्स असतील, त्याचा काय नो, देर इज नो रिलेवन्स ऑफ दॅट. आणि तुमचा जो पोर्ट ई आहे तो रेग्युलर सिम्पली ॲज इट विल वर्क ॲज आयो पोर्ट. पोर्ट डी विल ऑल्सो वर्क ॲज जनरल पर्पज आयो पोर्ट, right? But when you set this bit, you are going for PSP option. When you are going for PSP option, in that case your port D will work as PSP, parallel slow port, and that port will require handshake signals. Those handshake signals are stored or indicated by these 3 bits. You can see that these are 3 handshake signals. These are 3 handshake signals: IBF, input buffer full; OBF, output buffer full; and input buffer overflow are the 3 handshake signals. Okay, so that's how this particular bits will be used, particularly when this bit is 1. Right? As I told you before, when this bit is 0, these 3 bits are don't care bits. Is it clear?
Yes, sir.
Oh, okay. So that's all. Okay, actually we have to discuss the how port D actually works as parallel slave port. Of course, that we'll discuss next time, because it will take some time for discussing that. We have to discuss how the signals are exchanged. So today we can stop with this. तुमच्या काय शंका असतील तर बोला. कुठले ट्रीस हां हां हो 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 पोर्ट ए 6 बीट आहे. तसंच ट्रीस ए सुद्धा 8 बीट पोर्ट असणार बेसिकली. त्यातले जे 2 बीट शिल्लक राहतात दे हॅव नो फंक्शन. Actually they are not implemented, unimplemented. इथे म्हटलंय बघा, see here it is said that see what about bit 3? Bit 3 is unimplemented. Unimplemented म्हणजे actually there is no bit. म्हणजे you cannot set that bit or reset that bit. जर तुम्ही ते रीड केलं तर तुम्हाला 0 रीड होईल, परंतु त्या ठिकाणी ॲक्च्युली बीट नाहीच आहे. तसंच पोर्ट एच्या बाबतीमध्ये असणार. ट्रीस ए मध्ये जे त्या 2 बिट्स आहेत ते अनइम्प्लिमेंटेड असतील.